Hello, my name is Sanjay Baruah. I am a professor of computer science and engineering at Washington University in St. Louis. I had attended ISORC for the very first time last year when it was held in Valencia, Spain. And it was my experiences during last year's conference that motivated me, that encouraged me to submit the paper I will be presenting here today to this year's conference. Last year at ISORC, I saw significant participation in the conference from researchers working in two different subdisciplines of real-time computing: model-based design and real-time scheduling theory. I thought that was wonderful. I look upon these two subdisciplines as foundational cornerstones of real-time computing and believe that greater integration, closer collaboration is necessary in order to further advance the discipline of real-time computing. So one of my major motivations in submitting this paper for possible presentation at ISORC 2020 was to have an opportunity to make this pitch to you in person in Nashville, to argue for closer collaboration between research in model-based design and real-time scheduling theory. Unfortunately, of course, COVID-19 has intervened and personal pitches are no longer possible. I am forced to do this over the internet. Nevertheless, I hope that big picture message does go across. I sincerely believe that we must collaborate more closely across model-based design and real-time scheduling.
Let me start out providing some context and background. In developing safety-critical real-time systems, we are driven by two often rather contradictory concerns. On the one hand, since these systems are safety-critical, we must ensure that they execute correctly during runtime. Additionally, however, many safety-critical systems execute in highly resource-constrained environments, and we would therefore like to be able to implement them in a resource-efficient manner. In the early years of the discipline of real-time computing, these twin goals of correctness and efficiency were achieved by keeping things very simple. Safety-critical systems were restricted to being very simple, responsible only for very simple, highly repetitive kinds of functionalities. They were typically implemented as carefully handcrafted programs, often consisting of little more than straight-line code embedded within an infinite loop, executing upon custom-built processors that were especially designed to be highly predictable with respect to timing behavior. Now, these early systems were very successful in achieving the twin goals of correctness and efficiency, but things soon grew more complex. The functionalities we expected of our real-time system grew more complicated. These more complex systems required more computational power. They could no longer be implemented upon simple, predictable processors. It soon became very difficult for a single developer or a small team of system developers to reason about the correctness of a large, complex system in all its gory detail. Instead, abstractions had to be introduced that would highlight the relevant or salient features of a system's execution, while concealing the less relevant, the less important aspects. But in deciding which aspects of runtime behavior should be highlighted and which one concealed, we are driven by what we consider to be important. And here, the community of real-time systems researchers split into two sub-communities, motivated primarily by the fact that many real-time systems execute in highly resource-efficient and resource-scarce environments. Some researchers started focusing upon the efficiency aspect. Others, however, focused upon the fact that these systems were becoming increasingly more complex, and being safety critical, correctness needed to be ensured. They therefore focused upon assuring that correctness could be guaranteed, letting considerations of efficiency recede to the background.
In somewhat greater detail, in the early years of the discipline, researchers asked, what abstractions do we need in order to ensure that systems that are described using these abstractions can be implemented in a resource-efficient manner? More recently, motivated by the fact that these safety critical systems are getting to be so complex, the question that has often been asked is this: what are the abstractions that will enable us to design large, complex safety critical systems in a manner that gives us a great deal of confidence that the systems we have constructed are indeed correct as designed? The earlier work on resource-efficient abstractions gave rise to many of the very well-known models that are studied in real-time scheduling theory, such as periodic and sporadic task models for representing recurrent processes, models for representing various kinds of implementation platforms, priority-based scheduling algorithms, algorithms and protocols for networking that can make real-time guarantees, etc. The other abstractions, those focused on provable correctness, have come up with a completely different set of basic ideas. Perhaps one of the most important ideas here, one of the foundational concepts, is that of the synchrony hypothesis, which seeks to abstract away the notion of physical time altogether by introducing the concept of logical time and making the simplifying assumption, the tremendously useful simplifying assumption, that actions such as execution of code take zero logical time. Formalisms centered around the synchrony hypothesis that enable us to describe timed executions have been introduced, including the synchronous reactive model, timed automata, timed P-tree nets, etc. Model-based design methodologies built upon these formalisms have been developed. Many of these model-based design methodologies, which typically come equipped with very strong tool support, have proved extremely popular and are widely used in industry today, including in the safety critical industries of aviation and automotive systems. However, with this current state of affairs, we confront a bit of a conundrum. The earlier models, the ones that ensure resource-efficient implementation, are at a low enough level of detail that it can be argued that it's very difficult to design large complex systems using these abstractions and have a good deal of confidence that these systems are indeed functionally correct. Provable functional correctness can be achieved using the more recent abstractions. However, we do not yet know how to achieve resource-efficient implementations of systems described using these abstractions upon the current physical platforms that are available to us today. So I believe a foundational, very central research question that deserves further exploration is this: can we apply the methods, techniques, and results of real-time scheduling theory in order to achieve more resource-efficient implementations of safety-critical systems that are specified according to these more advanced, more complex model-based design abstractions that, as I have just stated, are capable of expressing more complex system properties, but currently lack resource-efficient implementation. So that was basically the main pitch that I wished to make here. I believe that much is to be gained by having real-time scheduling theory and model-based design play together. The remainder of my paper, the technical part, contains one example of such interplay between model-based design and real-time scheduling theory that I will now briefly describe during the remainder of this presentation. The synchronous reactive model of computation can be used to describe many model-based design methodologies out there. In this model of computation, a program is obtained by composing together multiple reactive blocks, where a reactive block can be thought of as an entity that accepts as input streams of data, processes these data, and generates streams of output data. In this particular example, the output streams out1 and out2 represent the input stream delayed by 1 and 2 time steps, respectively. The processing that occurs within a reactive block can also be represented using an alternate representation that is known as a task graph, which exposes the parallelism that may exist within such processing. A synchronous reactive program is obtained by composing together multiple reactive blocks. So for example, we may have these additional blocks and obtain a program by composing them by connecting outputs of the initial block to the remaining two blocks in the spanner. In synchronous reactive programming, it is assumed that execution of the system proceeds in discrete rounds or time steps, with an input being generated every round and outputs from the entire program being produced again during every round. All the reactive blocks are assumed to execute once during each round. And of course, all of this happens under the synchrony assumption. The synchrony hypothesis, if you may recall, states that actions execute instantaneously. They take zero execution time. And why this assumption, as I had mentioned earlier, makes a lot of sense and is very convenient an abstraction from the logical perspective, it is, of course, not true on actual platforms. Execution of code does take non-zero time of real time on physical platforms. So the specific problem that I looked at in my paper that appears in your copy of the proceedings can be described in the following manner in the context of our simple example here. I want to obtain an efficient implementation of the first block in this example, the block that's outlined in red, given that the duration of a round would take d units of real time, and that I'm given implementations of the remaining blocks, the blocks represented here as by and bc, and these implementations take dy and dc units of real time, respectively. In the paper, I have identified a relationship between this problem of implementing synchronous reactive programs and one of scheduling directed acyclic graphs upon multiprocessor platforms, when the directed acyclic graphs may have deadlines associated with individual nodes of the graph, individual vertices of the DAG. Now, scheduling of DAGs is a very widely studied problem in scheduling theory, and this mapping from implementing synchronous reactive programs to DAG scheduling allows us to adapt and adjust many results from scheduling theory to obtain more efficient implementations of synchronous reactive programs. A specific form of optimization that I looked at over here was the following. How can we minimize the number of processors that we need to devote to an individual synchronous reactive block without having it violate its timing constraints? And the results that I was able to obtain with regard to this particular implementation issue are as follows. I was able to obtain an algorithm that determines a certain number of processors and is able to guarantee that this number of processors is indeed a safe number to assign to the reactive block. By doing so, we would ensure that deadlines are never missed during runtime. I was also able to quantify the effectiveness of this algorithm via the speed up metric by showing that the number of processors determined by our algorithm would be no larger than the number of processors that could be determined by an optimal algorithm, which had access to processors that were approximately half as fast as the processors available to us. And that's pretty much all I had to say. Let me reiterate the main points. I believe that in implementing safety-critical real-time systems, we have to be concerned with both correctness, of course, and efficiency, because these systems are often implemented in resource-constrained environments. While model-based design techniques have focused on assuring functional correctness, real-time scheduling theory has for decades been concerned with issues of efficient implementation of timed systems. The research question that I believe merits exploration is this: can we apply results from real-time scheduling theory to obtain more efficient implementations of systems that are designed using model-based design techniques? I used a small illustrative example, which seems to indicate that the answer to this question is certainly, at least for this example, yes. Thank you for your attention. I'm, of course, happy to take questions via email. Thank you.